So let's look at some slightly more challenging fundamental theorem of calculus part 2 problems. Okay. So again, remember our relationship here. We take the derivative with respect to x of this integral from a to x of f of t dt, and what do we get? We get back to the function f of x. Essentially, we're going to see this inverse relationship, right? If I integrate the function little f, and then I take the derivative, I'm right back where I started from. There's a slight little change in the variable, obviously, because here inside the integral we need this dummy variable, different than x, right? Now, this is clear as long as what? The lower limit is a and the upper limit is x. But what if that's not the case? Here, the lower limit was a constant, 0, and it could be actually any constant, provided, of course, that this function is defined in that integral, right? We won't want to have a function that's not defined in that interval. But what if this is not a constant down here? Or what if this is something other than x, like this example? Now here we do have a constant. Again, pi over 2 is a constant, so that's like a. But instead of x, we have x cubed. So how are we going to attack this? Well, I mean, there's a couple of ways of doing this, and I'm just going to do it this way. I'm going to say, okay, let's go ahead and use the fundamental theorem of calculus part 2 inside here. If I were to find this, I would need to know the antiderivative cosine of t squared. The problem is I don't know what the antiderivative of cosine of t squared is. But I don't need it to answer this question. I don't need to know what it is. I'm just going to say, I'm going to let capital F prime be equal to cosine of, you could say t squared. I'm going to go ahead and say x squared. Okay. Notice this is not, this is cosine of x squared. Right? The cosine of t squared. It's not cosine squared x. There's a difference there, right? So here you square the x first, and then you plug it into the cosine function. Okay, so I'm going to let f prime be that function. So it's the antiderivative, right, of cosine of t squared, right? Just changing the variable. So what do we have? We evaluate by fundamental theorem of calculus part 1. We evaluate to this definite integral. I integrate. I evaluate this antiderivative at what? The upper limit minus the evaluation at the lower limit. And then I take the derivative. Now, remember, this is just what? Cosine of pi over 2. This is a constant. And when I take the derivative of a constant, I get 0. So that term, the derivative is going to be 0. So I just have to focus on this one. But what do we have here? This is not f of x. This is f of what? X cubed. So what rule do I have to use on this one in order to find the derivative? So here I must use what rule? What rule from Calc 1? The blank rule. What is it? You said chain rule. Give yourself a cookie. That's good. That's what it is. Chain rule, right? Got an outer function of capital F, inner function of x cubed. So what's that derivative going to be? This will be equal to, so all this stuff here that we dealt with, the derivative of this is going to be what? F prime, the derivative of the outer function, right? This is chain rule, derivative of the outer function, evaluated where? At the inner function, which is x cubed, times the derivative of the inner function. That's the chain rule, right? Derivative of the outer function, evaluate the inner, times the derivative of the inner function. What's the derivative of the inner function? That's pretty easy. Derivative of x cubed is just 3x squared. Okay. And what is f prime of x cubed? Well, I know what f prime is. I don't know what f is, but I know what f prime is. It's the antiderivative of cosine of x squared. Or I could do cosine of t squared here as well. But I'm going to replace the input here with what? With x cubed. With x cubed. And so notice this is going to be cosine of what? Plug in x cubed for x, I get x cubed squared. Right? So that's f prime of x cubed, right? Replacing x here with x cubed. And so cleaning all this up, what do we get? I'll put my 3x squared in front times cosine of what's this? X to what power? What do we do with those exponents? I hope you say multiply cosine of x to the 6. Emphasize that that's cosine of x to the 6, and there's your answer. So we have to imply the chain rule, invoke the chain rule, if you will. Okay. Let's look at another example. Okay. This time, the lower limit is not a constant, right? And the upper limit is not a constant either. Right? But I'm going to proceed the same way that I did here. Again, I'm going to work inside here with the fundamental theorem of calculus part 1, and then I'll take the derivative. But I'm not going to find the antiderivative. I don't need it. Okay, so again, I'm going to let derivative of capital F be the square root of 4t squared plus 1. I'll use t this time. It doesn't really matter, you know, the variable, because we're going to plug in, like we did over here, we're going to plug in, you know, some function of x. So then this is what? The derivative with respect to x of the antiderivative, which is capital F, evaluated what? At the upper limit of 4x minus the antiderivative evaluate the lower limit. Now when I take the derivative, what do we get? We get, here is chain rule, right? F prime of 4x times the derivative of the inner function, which is 4x. Now what's the derivative with respect to x of 4x? That's pretty easy, it's just 4. And then minus here, this is just f prime of x. Just straight up f prime of x, because there's x in here. Over here we got a little chain rule, right? And so what do we have then? We have, this is equal to 4, let's bring that in front. What is f prime of 4x? Well, f prime of t is equal to 4t squared plus 1, so I'm going to replace t with what? 4x. So be careful here, it's t squared, t is 4x all squared plus 1, minus f prime of x, well that is just going to be replace t with x, 4x squared plus 1. And I can clean this up a little bit here. 4 squared is 16 times 4 is 64. So I'm going to have 4 times the square root of 64 x squared plus 1 minus the square root of 4x squared plus 1. Not really much I would want to simplify more there, right? But there it is. You know, crazy result, but that's what we have. So again, notice in the process, I don't actually know what capital F is. I don't care. I don't have to. I mean, if you could find it, you could. That's fine. You don't have to. Okay. So all these problems can be done that way. Okay. But that is how you find derivatives with that fundamental theorem of calculus part 2. Okay. Let's take a look now at a more graphical example here, see if we understand the relationships that we've been talking about. So here I have a function. Y is a function of t here, and going from -2 to 4 is our window here. We're going to let g of x now be the integral from -2 to x of the function f of t dt. Okay. And we're going to find the following values. So first of all, we'll just say, what is g of 0? So g of 0, well, I mean, you can plug in to the function. Notice the input to the function is the upper limit, so this would be -2 to 0 of f of t dt. All right. So what's that going to be? Well, we're going to use the graph to do that. What's the area under the curve from -2 to 0? Well, the function is above the x-axis over that interval. So we're talking about this area here, which is some positive area, right? And in fact, what is that area going to be? It's the area of a rectangle, area of a triangle, right? Which is 1/2. The base is 2, and the height is 2 as well, right? So that's 1/2 of 4 or 2, and so there's my answer. G of 0 is 2. What about g of 2? Well, that would be the integral from -2 to 2 of f of t dt. Okay. Now, we're going from -2 to 2, we've got this area, plus I've got this area here, right? Which is also positive, notice. So I know I've got the 2 from the blue area, plus I've got this purple area, which I'll break up into 2 parts. Here I have a rectangle, which is 1 wide by 2 high, 1 by 2, so 1 times 2. I'm going to add 2 units for that. And then area of this triangle, 1/2 base is 1, height is 2. 1/2, 1 times 2 is equal to 1. And so this is 5. That's that total area. All right, so again, you can see how we're treating this accumulation. This is the area function of accumulating area under this curve. Now if I go to g of 4, of course, g of 4, that's the integral from 0 all the way, not 0, -2, excuse me, -2, to 4. -2 to 4 of the function. Okay, so obviously going from -2 all the way to 4, we've got all this area we've already found, but plus I'm going to go all the way to 4, but notice the function's below, and so now what? This region is negative area down here. And so I've got the, from -2 to 2, we already know is 5, so we've got the 5, and then I'm going to subtract this area, right? Which is what? Area of a triangle again, with a base 2 and a height of 2. 1/2, 2 times 2 is 4, so I'm going to subtract that 1/2, 2 times 2, which is minus 1/2 of 4, or 2 rather. So -2, so 5 plus a -2 is 3. So that's the way you can accumulate area graphically. And then let's take a look at derivatives. Okay, well, what's the derivative going to be? Well, this is where the fundamental theorem of calculus part 2 comes into play, because notice g prime of x, right? Do we have a formula for that? Well, it is, if this is g of x, then this is the derivative with respect to x of the integral from -2, a constant, to x, f of t dt. And we know what this is, right? By the fundamental theorem of calculus. That's part 2. We just proved that in the first video. This is just f of x. Just f of x. So the derivative is just the value of the function f at x. What graph is this? Is this the graph of g or the graph of f? It's the graph of f, right? This is the graph of f. So guess what? This is the graph of the derivative of g. If g of x is equal to this is the graph of the derivative. So what is g prime of 0 from the graph? This is g prime. Input 0, what's the corresponding output? 2. Right, so it's just f of 0, which is 2. So g prime of 2 is going to be f of 2. What's f of 2? F of 2, what's the output? 0. G prime of 4 is f of 4. What's f of 4? Input 4, where's the function at? Down here at what? -2. Okay. So the big picture then again about the fundamental theorems of calculus part 1 and part 2 is that we have inverse operations. So again, if I, inside here first, if I integrate, right, fundamental theorem of calculus part 2 basically says if I integrate and then I take the derivative, I get back to where I started with. I start with function f, I integrate it, and then I differentiate it, I'm right back to f. Okay. Fundamental theorem of calculus part 1 says what? Another way of saying it is this, right? If I'm integrating from a to x, the derivative f prime, what's the antiderivative of f prime? That's f, right? Then it would be the antiderivative, which is f evaluate the upper limit minus the evaluation of the lower limit, right? And so you see what we're saying again here. If I first take the derivative inside here of the function f and then integrate, I get what? Back to the original function. Oh, by the way, what's this? A constant. So remember, anytime we integrate, we always get that constant. So when we take the derivative, then integrate, we get back to the original function, plus or minus a constant, right? There's some constant there, and that we can't get away from that. But essentially, that's the idea. Okay, so in the next one, we're going to review a little bit from Calc 1 and look a little bit more at this from a graphical perspective.